moving on to part C. So now knowing this problem, this like fatal error in our function, we want to actually fix it. So we want to give checksum a string and know that for every string it will have a unique output. No other string will have that same output. Okay, so going back to this example, CAB should return one number and BCA should return a different number. Okay, so notice here that the example failed because it didn't take into account that the letters could be in different positions. Alright, so even though they're in different positions, you still get the same sum. So that should signal to you that a fix needs to take care of the positions in the word. We should at least account for it in some way, be thinking about it in our code. Okay, so getting started. Assume that there are only 9 letters in the alphabet, A through I, and each with the same letter value as before, A as 1, B as 2, so on and so forth. And also assume that a given word cannot have any duplicate letters. Implement an improved algorithm in which every valid input reports a unique output. And explain how your algorithm works and how it fixes the problem from our original checksum. Alright. Okay. So how do I want to go about doing this? You know what? How about we just copy over our code from here. Alright. I'm going to paste it over here, and then we're going to make changes to it. Alright, so instead of writing from scratch, I think it's good to look at what you had and make it better. Okay. So we first have our sum, our list of letters, things like that. Alright, so the key thing here is that we want to be changing what's in this line, right? How we implement the sum, how we're adding the letters together is really important, and that's going to be the way we fix the algorithm. Okay, so we want to do something with the positions, so that with like the word CAB, we wanted to, you know, sort of keep track of the positions of the B, the A, the C, and give me some value X. And when we have A, C, B, we keep a track of the differences in the position, and then this gives us a different value of Y. Alright, so knowing that, I want to code for the position in some way, and you can actually tell, because we give you these helper functions, pow and pause, you should probably be using them and thinking about how they can fit into your code. Okay, so I'm just going to write the addition that makes this question correct, or this implementation correct, and then explain it afterwards. Okay, so not only do we want the letter's value, we want to times it by 10 to the power of the position of the letter. Sorry, I'm just gonna squeeze this in. Okay, there we go. Okay, so I'm gonna walk through an example of this. Oh, you know what? Let's just try it with the word ace. Okay, so this will be our example box. Okay, so first sorry, not total, it's actually called sum. Our sum is 0, right? But then we go through the list of ace. So L becomes this. Alright, looking good. And we go through all the letters starting with A. So sum becomes not 0 anymore, but instead 0 plus the letter A's value, which is 1, and then times 10 to the position of the letter. So remember that the positions of always start at 0, so A starts at 1, C is at 1, or sorry, 0, can't talk. A is at 0, C is at 1, and E is at 2. Alrighty. So that gives us 10 to the power of 0. Alright, so this should be just 1. Okay, and now we move on to C. So I'm gonna scratch this out. This becomes 1. Right, because in this line, when we say sum plus equals, this means we want sum to be whatever it was and plus this additional line of code. So we keep the 1, do 1 plus the letter value of C, which is 3, and then times 10 to the position of C. So that's 1. Right, so that's 30 plus 1, which is 31. And then we do the same for the last letter, which is E. Right, so this is 31 plus the value of E is 5, so this is 5 times 10 to the 2, so this is 531. Right, so the value of ACE is 531. Okay, something I want to call your attention to here is that this part of the code is giving every position, every letter, a new position in the value. So what I mean by that is for A, it was in the 1's position, right? We just had 1. Then for C, we had the 10's position, so it became 31. And for E, it had the 100's position, 531, right? And that has to do with the fact that we're timesing it by 10 to the power of the position. So for every position, it gets a new spot in the resulting sum. Okay, so that's really crucial here. We're taking account of the position and reflecting that in our actual answer. So that's the ultimate fix of our checksum algorithm. That's what helps it become unique for every string that we give it. So just to be really, really sure, let's mix up the letters of ACE and do CAE. Alright, I'm going to go through this a little fast. Okay, so sum becomes 0 plus 3 times 10 to 0, which is 3, equals 3 plus 5 times 10 to the 1. This is 53. And then this becomes 53 plus 1 times 10 to the 2. Right, so that's 153. Alright, so you can see here that if we change the order of the letters in the word, it must also change the order of the values in the sum. Right, and that's because we took into account the position of the letter into our summing algorithm. Okay, so you can see here that it does produce unique outputs for any unique input. And that concludes our algorithm and the correctness of it. So your answer to this question would be sort of talking about how this part over here, this wonderful part, fixes the problem that we had in our checksum, which is that you could have these two examples or things like it and still get the same value. This is not what we want. We want different values for different words. Okay, so just to really drive it home, we need to take account of the position of letter. Alright, so until we had done that, we were not actually creating unique outputs because of the way we could resort the letters in the word. Alright, so that is checksum.